So first, as always, you have a, if you ever had a dream about asking question about stochastic calculus, now it's a perfect moment to realize.
May I ask a question?
Yes, yes.
So expectation star of exponent sigma winner process star t.
Sorry. Exponent process sigma.
Winner, yeah.
Uh-huh.
T is equal to, given f0.
Given f0, yeah.
Wait, 0, sorry. Is equal to exponent sigma square over 2t, right?
Exponent sigma squared over 2t. Yeah.
But if we, for example, have not f0 but f1, it would be different, right?
Yes, it would be different. Yeah.
So would it be like exponent star the same? Given f1, is it like exponent sigma w1 star? Exponent.
Oh, almost. Yeah. Times something. Yeah.
I had like exponent sigma w1 star plus sigma square
Okay,
over 2t.
Let's solve it. It's a good question because the technique is the same. We have applied it. So basically, the idea is to represent future as current future value. Like we have used this idea, it's current value plus change. And in our case, change is independent. So for winner process, the future change, the future increment by properties of winner process is independent of what we know. So it allows us to make something like expectation star exponent sigma wt star minus sigma w1 star plus sigma w1 star. So I've done nothing. And basically this I represent as a product of two exponents, wt star minus w1 star, and everything given f1. So the first term is known. And so I can do what?
Take it out of the expectation.
Yeah, take it out of the expected value. And if I'd like to work with the second term, I saw that is independent.
Yes.
Independent. And so basically it's exponent times expected value of exponent of sigma wt star minus w1 star 1, 2, 3. Yeah, because I can omit sigma algebra f1 because they're independent.
Yes. But wouldn't there be like, if we would do the same with as well, sigma squared over t, like what do we usually have in Black-Scholes model? There will be just so
what is the question?
Expected value sigma w star t minus sigma squared over 2t given f1.
sorry, sigma square, sigma, once again, expected value.
Minus sigma expectation or exponent as well in
No,
under.
From the beginning.
Yes, okay, expectation of exponent sigma w star t minus sigma squared over 2t given f1.
So basically we need to go, but why do you have standard expected value? Because when you,
Star, it's expectation star.
but basically the technique is the same. So
Yeah,
this is
and it will
constant,
be just
non-random. And so you can move it out of expected value as it is non-random.
so this exponent of minus sigma 2 over 2t will be just additional term, like on the right hand side.
Because it's non-random.
Yes, I mean the answer will be that second
The answer to what?
to this expected value will be 1 second. Will it be like exponent of minus sigma w1 star plus sigma squared over 2t?
I don't remember answers by heart.
I mean,
so
given what we had.
We need to finish all the calculations. So we need to finish that one and to multiply it by this exponent.
Wouldn't be exponent star of expectation star of the exponent sigma multiplied by increment? Wouldn't it be 1?
Why it's 1? No.
Isn't no? Or I mean,
so we need to honestly check this, because okay, let's continue. Let's make it. So we need to finish only that guy. Yeah. So we continue with this expression.
yes.
We need to calculate expected value of exponent of sigma wt t minus 1 star. And basically this has distribution like wt star t minus 1. Yeah.
And why is that?
Why is that? Because the law of this under probability star is just normal random variable with mean 0 and variance t minus 1. And this is also normal random variable with mean 0 and variance t minus 1. They are not equal, but the law, the distribution is the same. So I don't say,
okay.
So be careful. I don't say that this is the same thing as, so these are not, they are not equal, but the distribution is the same. Wt star minus w1 star is the same. That is normal 0 t minus 1, and this is normal 0 t minus 1. So yeah, they are not equal as random variables, but they have the same distribution. But when you calculate expected values, you don't care about random variables, you care more about distributions. Okay? So we can just do it like exponent star of exponent sigma wt minus 1. Okay? And that is equal to sigma squared to, to exponent sigma squared over 2 t minus 1.
Okay. Mm.
Okay.
Okay.
Any more
Good.
questions?
Boris Borisovich, could you please once again explain the strategy of finding the price of an asset at time 0 in Black-Scholes model? So we should do like you now did, just get everything that is non-random from the expected value and then
The
deal with
strategy.
what remained?
The strategy. Calculate expected value. You need only to be able to calculate expected value. That's all. How do you
Yes,
calculate expected value? You take integrals, you use properties of expected value. It's up to you.
yes, but I have a question like this. So should we take at first everything that is non-random out of the expected value and then calculate? Or should we try to make a martingale instead the expected value, inside of the expected value, and then calculate?
We are in a free country. Russia is a free country. You can use martingale properties. You can do integrals. You can take out constants of expected value. We're in a free country. You are a free
Okay.
girl, and you can do anything to calculate expected value. So you should. So you may. So it's not forbidden by government to take non-random quantities out of expected value. Okay, you can do this. So you can. So for example, if you see that there is some k that is constant something r that is random given f0, so you may take out k out of the expected value, or so you may use this property. You may use so you may say, oh, but just this is an integral, yeah. The only thing, so imagine that R is independent of F0, imagine like this, because we can always do some transformations in the other case. So it is ordinary expected value. And then you say, oh, I will take integral from minus infinity to infinity k times R times density function of R dr. Okay, you can do integral. Sometimes you can use martingale properties. If you see that there is RT times AT times, I don't know, so there is K times RT given F0, and you know additional information, then that RT is a martingale with respect to Ft under P star. And in this case, you may immediately say that this is K times R0, okay?
Mm-hmm.
And
Okay.
this is very fast. So basically, you can use other techniques. So any honest approach to calculate expected value.
Okay, thank you.
Calculate expected value. So I think that we all will give us the same answer if they are done correctly. I think the fastest one, if you see a martingale, obviously, if you see a martingale, then obviously it's faster to use the third one because you immediately get the answer. But in many times you don't see a martingale. So I think this is the fastest one. I think this is the fastest, but it's not always applicable. even if you see something like expected value, you have a RT times some QT given F0, and you know that RT is a martingale on the P star, but you have this guy, and oops, you cannot. If you multiply a martingale by some factor, it may still be a martingale, but it may not be a martingale. So, for example, in our previous case, as far as I remember, something like a martingale was multiplied by indicator, yeah, by random variable. And oops, it's not a martingale, you cannot use martingale property. So basically, it's up to you how do you calculate expected value. Either, no, but you should respect the properties of expected value.
Okay, thanks.
Otherwise,
May I ask another question?
Yeah.
So in Black-Scholes model, R is our interest rate, but what is mu exactly? When we think not under star, but under just P.
So
we had there that mu.
So let's look
blah,
at the
blah.
equations. Let's look at the equations. So dst is mu st dt plus sigma st dwt, and dbt is r bt dt. So we have two assets. One is risky. The second one is risk-free. And basically, yes, R is risk-free interest rate. And if we solve this equation, we have st is s0 times exponent mu minus sigma squared over 2t plus sigma wt. And we can see that share price can be decomposed into the product of s0 times exponent of sigma wt minus sigma squared over 2t. Oops, too much brackets. Multiplied by exponent of mu t. And here we can see like the sense of mu. So what is st? It's a martingale. And the probability measure P, original true one, not artificial, but real life probability measure. So without this term, the expected value of st would be constant. Okay. And
so is it like a growth rate of this risky asset?
It's a risky interest rate. So we can calculate expected value of st, and expected value of st ordinary non-star given f0. This is a martingale. So the expected value of that part is just s0, as it is a martingale, times expected value of mu t.
So kind of like return on an asset.
Yeah. It's a risky rate of return.
Thank you.
Okay.
Boris Borisovich,
Yeah.
may I have a question? May I ask you a question, please?
Yes.
I have a question about the expectation. How did you calculate the expectation of the difference of margin of not martingales but winner processes? Just two pages up. Yes, this one.
So first step, I have done two steps. First step is to say that step one, to say that the distribution, when I calculate expected value, I don't really care about the random variables. I do care more about the distributions. So the name of the variable is not important. Expected value of Z, expected value of W, expected value of S. If I know that the random variable has normal distribution with mean 5, then I don't care about the name of this distribution of the random variable, okay? So the only thing that matters is the distribution, yeah?
Mm-hmm.
So, and I recall the properties of Wiener process that this difference has normal distribution 0, t minus 1, and that random variable also has distribution 0 and t minus 1, okay?
Yes.
So I can replace inside my expected value, I can replace difference by one random variable, okay? I don't say that they are equal, but I say the distribution is equal, okay?
Yes, and how then you calculated this expected value?
Okay, so that's the second step. I refer to the result. So step 2, how to calculate expected value of exponent sigma w star t. Okay, so the question is how can we calculate this value? Okay.
Yes.
So basically, it's the same thing. If I drop both stars, yeah, because what is important that guy is normal 0t under p star, and I use p star. That guy is normal 0t under probability measure p, and p is used there. Okay, so the
Yes.
idea they are equal. Okay, and if you consider we have proven, so I will state result. So I'm using the following result. If Wt is a Wiener process under P, then Mt equal to exponent of sigma Wt minus sigma squared over 2t is a martingale. So we have proven that result. It's not hard to prove it from 0. So how the proof is very easy. I just calculate dmt, and dmt will be, if I take the derivative with respect to t, it will be minus sigma squared over 2 times exponent of sigma wt minus sigma squared over 2t dt, plus, if I take the derivative with respect to w, I will get sigma exponent of sigma wt minus sigma squared over 2t dwt plus 1 over 2. If I take the second derivative, I will get sigma, once again, sigma squared exponent of sigma wt minus sigma squared over 2t dwt squared, okay? So
Yes.
I have used Ito's lemma. So I see that these two terms will cancel out, okay? Yeah.
Yes.
Yes.
So dmt is sigma mt dwt. So I see no dt term. So mt is a martingale.
Yes.
Okay, so we have proven our statement. We can draw a black square, happy black square, very happy black square. But if MT is a martingale, then expected value of MT is constant. It's like expected value of M0, expected value of M5, M3. And M0 is just 1. If you just plug in 1, 0, okay?
Yes.
So expected value of exponent sigma wt minus sigma squared t is 1. Expected value of the product of these two exponents is just 1. I can take out this exponent and I have expected value of sigma wt is expected value sigma squared over 2 times t.
Yes.
That's all. That's what you need to calculate. If you change t by t minus 1, so expected value of sigma t minus 1, if you just change, so it will be expected value of sigma squared over 2 times t minus 1.
Yeah, I see now. Thank you very much for the explanation and derivation.
Okay, any more questions?
Boris, I have a question, but not about material, but about additional readings. So you recommended us books by Zastavnyak, for example.
Yeah.
Those are books. Maybe you can recommend any lecture notes to read.
I have posted lecture notes by Zervas, who was reading this course a long time ago.
In the Telegram channel, right?
Yeah, I can post it into ISF system if you wish. It's not a problem.
Okay, but if they're in the Telegram channel, okay, thank you. Maybe I missed. Thank you.
So you can just let me find it. But I'm sure I have posted them.
Yes, you had.
So
It's in Telegram chat.
yeah. But I don't. Where it is? So, but I know. I think I have. So there are many other notes. So that's a little bit hard with stochastic calculus because it's rather tough from mathematical viewpoint. If you do rigorous mathematical stuff, then you need to know measure theory, and I try to choose approach to avoid to introduce sigma algebra sigma algebras, but to skip about measure theory. So that's my approach. Maybe it's not good. I don't know how it would be from methodological viewpoint to do better, because the time is limited. I have, let's say, 6 lectures or 7, something like that. And so my goal is to go from sigma algebras and finish. So the starting point is clear, and the final point is clear. Black-Scholes model and pricing simple European claims. But the way, okay, so you may find what else? What else? Open notes without books. What else? You have notes by Ivan Wild. Also, I think, let me copy. You have
Ivan Wild, you said?
I will post Ivan Wild at the
Okay, thank you.
stochastic analysis, but they are more stochastic calculus. How to find it? Ivan, but they are they are good, but they are what can I think this no. What else can I do? One wild. You have also chunks. There are many chunks. Draw chunk. Yeah. So this has something about martingales, chunk nodes. Chunk nodes. What else can I do? Ooh. Or we have also, I think that is one is also good by Kellen. So what else if you don't wish to buy books? I understand you. Of course. This is more, so this has processes with jumps, but okay. I think it's more, okay. I think just like this. You have also Pollard. It has martingales, Brownian motion. Okay, that's all. But basically, if you speak of, there are many others, so you can Google by yourself. I think these are more or less appropriate. So they are not specially designed for our course. So it would be wrong to say that they perfectly cover what we have covered and they have nothing more. Maybe they do not cover some small topics we cover, or they cover a lot more in other directions. But basically, they're, let's say, if you understand any of these notes, then you for certainly will pass and probably will get very good result. Yeah. So if you'd like about open lecture notes, so, okay. Other questions?
Boris Borisovich, can I ask a question in Russian?
Yes. Yes, I will. I don't know if there are any non-Russian speaking students.
Okay. Can I send please to you the solution of homework 3? Number 2, like, can you please check whether I'm doing right or wrong or something like this?
I don't recall the deadline. If the deadline is passed,
No,
we
I mean
can
it's
discuss
homework
it.
homework 3. I mean question 2. Just I will send you the solution. Can you please check whether I'm doing right or wrong?
Deadline.
Uh,
So it's in few
so
days.
I don't understand. The deadline is passed or not? I don't
Not
recall.
passed. Not
Not
passed.
passed. So I can't comment whether you are doing right or wrong with the home assignment. So I can give some hints, but whether I'm doing right or not, it's too much. So no.
Okay.
After deadline, we can discuss in details. But before deadline, so something general publicly. So the problem with when we discuss a home assignment with when the deadline is not passed, then we should do it that anyone can see in the chat where everyone is present, and my hints are just limited because yes, I can solve every problem in the home assignment, but I don't like to do it before the deadline. Okay, so you may ask your question in the chat, and I will see whether I
Okay.
can give you some
Thank
tips,
you.
because otherwise it would be strange a little bit.
Okay.
Okay,
Thank you.
so any more questions?
May I also ask a question?
Yes. That's my,
But
because we have more or less, we have some topics about delta hedging, but more or less we have, because of online situations, the speed is a little bit greater. So when I'm writing something on whiteboard, there are more stops. So we have time. So you should ask questions.
I'm just interested in whether you will post hints
Yeah.
for the
I'm downloading. So it takes a lot of time. So I'm downloading from Zoom right now some lectures to post it on. So I download. I need to re-upload them on YouTube and so on. Yes.
Okay, that was my question, because I had right solutions for the first home assignment, but I'm not sure whether it's good in terms of time. Probably the task can be solved in a more time-saving way. That's why hints would be very useful.
Okay, so if the deadline is passed, we can openly discuss it. If the deadline is not passed, so you can ask in the chat, and I will see whether the hint is my hint is okay, or if it's too much. So,
Thank you.
if the deadline is passed, so no problem. We can discuss. I can give you hints and discuss my way to solve it. Maybe you will discover faster way. I don't know. It's
Boris, then
yeah.
can I ask a question about the home assignment number 2? The deadline has already passed.
Yeah, no
And
problem.
the question about the first problem, point B. So there was, as you may remember, there was a question about whether the processes are martingale.
Just let me open it. It will not take too much time. So okay, home assignment 2, yeah.
So the question about the first task,
Uh-huh.
about whether the process MT and KT is a martingale. So about MT, it's quite straightforward that it is a martingale. But what about KT?
So this is the point. Sorry, second assignment point.
Point 1B.
But you may construct and try whether you can construct as a Martin as a counter example, and obviously. So let's try to provide a counter example. Yeah.
Win a process, for example, and win a process multiplied by win a process is not.
Yeah, like this. Yeah, you may, for example, so B. So if you solve, so that's a good example. I think you maybe even the simplest one, the fastest. So if you take xt is wt, and yt is the same,
Well,
just equal to xt.
Борис
cannot see your
Борисович,
board.
you
Yeah, we
stop
cannot
sharing the
see.
screen.
It has switched off because of time. Okay, like that. So the question was, so just to a small recall, the question was, we know that xt is a martingale, yt is a martingale. Nothing said about whether they are dependent or not, so it's not written. And so we only know that xt is a martingale, ft is a martingale with respect to the same filtration. And the question is, kt equal to xt times yt is a martingale. And the answer is no, because not always, at least. Yeah. So
But
we
when
can take wt, yt equal to wt, and in this case, kt will be wt squared. And we know that expected value of wt squared is t, and so it's not a martingale.
Okay, thank you.
but if xt and yt are independent, this would be a martingale.
I think not. Not always. I think no. Let's try to. It will be a little bit more difficult to construct a counterexample, but I think I feel the answer is no. Let's try. It's a good question. 1b. You know that xt and yt are independent martingales. Ooh, let me see.
But what if they are orthogonal? I think when both of them are kind of like independent, and the product of two independent martingales should be, I think, I don't know.
So let's imagine that we know that x1, x2, all x are independent of all y. So let's imagine the case when all x and all y are independent. Can be said about x, y. I think. Yeah, let's imagine that. I think. Yeah, I think we can construct the following example. Imagine like you start at 0, 0, and xt is xt minus 1 plus, let's say, at. At is just minus 1 or 1 at random with equal probabilities. So at minus 1 or 1, and probabilities are 1 over 2, 1 over 2. And I think yt is just, so you basically go at random directions at every step. Let's check whether this will be, I think it will not be a martingale, but I'm not sure for the moment. But let's check. I think it will not be a martingale. Plus bt, and bt has the same properties, and all of them are independent. And let's check the expected value of xt plus 1, yt plus 1, given ft. So we have used the fact that to check that a process is a martingale, we need to do only one step in discrete time. Okay, that will be no, it will be It will be n because it's xt yt plus at plus 1 xt plus bt plus 1 yt plus at plus 1 bt plus 1 given ft. That one is xt yt. That one, yeah, that is 0. That is 0. That is 0. Okay, this one is a martingale. So we need to. So it's a little bit harder. I'm sure that we can provide an example, but the example should be a little bit subtle. So it's a good question. Yeah, good question. Good question. I'm sure that this is possible because we know that xt and yt are independent, but when we make a condition, so I think using some condition like x t plus 1 yt plus 1 given ft, this may make them conditionally dependent, I think. Yeah, it's necessary to do some conditional dependence. Yeah, like that. Yeah, we need to speak. So what can we do? So okay, I don't know the answer for the moment. If I modify this, if I add one more condition, so it's a good question. I will think about it. Maybe if I will find a solution in, I don't know, in some minutes, I will tell you. But I don't know for the moment. I don't know.
Thank
for the
you.
moment. So if I change a little bit the text, I'm not sure. So in the original text, it was not required that they are independent. And how the answer will change, I don't know yet. But I feel that I can make them dependent using some more. So my idea is that something like that. My idea that the answer is still no. And idea is like this. I have three processes, xt, yt, and some zt. And my idea is that these two are independent. And when I know, my idea is to construct something like when I know xt, zt, and yt, that should be xt. So that is my idea. I don't know yet whether I will succeed or not. If I do the same thing for yt, I need yt. But when I make a product, t plus 1, t plus 1, then something with z appears because that has some information about the product. So that gives me no clues about x, that gives me no clues about y, but this z, which is dependent of x and y, it contains some information about the product. So my idea is the following. But I'm not sure yet. But I believe the answer is no. Believe. So it's a good exercise. You may try to solve it, but I don't know the answer yet. I will think about it. It's funny. I like it.
Boris Borisovich, may I also ask one more question?
Yeah.
Is it possible to prove that expected value of the difference between two winner processes, Vt minus Vs cubed given Fs is 0.
Yes.
But how?
No.
This is because
You
like
have first. Yeah.
odd central moment of normal distribution is 0.
Yeah. First idea that you don't care about the random variables, you care about the distribution. So it basically the same thing. It just I say Z has normal distribution with mean 0 and variance t minus s. What is the expected value of Z cube? Yeah. So first question: when you calculate expected value, you don't really care about the names, whether it's a Wiener process or pum process. You care about the distributions. Okay. And how can I calculate that? I can, so I have two choices. I say it's symmetric about 0. Okay, so symmetry about 0. So intuition says me symmetry about 0. And so it should be 0. If you like some honest calculation, you may always do integral from minus infinity to infinity, z cube 1 over square root of 2 pi t minus s exponent of minus 1 over 2 z minus 0 squared over t minus s dz. And basically you see that this is a function. So you are now integrating a odd function. So this is z and this is the integrand. So it looks something like that. And if you'd like to calculate the total area, that part of the area would be count with plus, and the symmetric part of area will be count with minus. They are equal because the function is symmetric, and so it's 0.
But is it possible somehow to prove the statement by the increments? So future value equals to
what?
current value plus the increment.
But we have used this property. We have used that future increment has normal distribution. We have used this property. Either you say because z cube is symmetrical about 0, this distribution is symmetric about 0, so the answer is 0. Either you use intuition, either you go to, so we have already used the fact you mentioned. We used the fact that this random variable is independent of fs, so we can omit fs. There are no conditional so this is unconditional expected value. So the fact you state we have used it explicitly. So why have we dropped? Why there are no sigma algebra there? Because that increment is independent. So we have used.
I see it now. Thank you very much for the explanations.
Okay. Any more questions?
May I just clarify that the expectation of an Etos integral always 0, right?
Not always. There are some technical conditions. So it's the price we are paying for short time and non-rigorous course. So if so basically you can imagine an integral and it is integral that is not a martingale. You can do that. But provided the integral exists, provided that expected value of let's say t expected value of a u squared du is a constant, and in this case, when provided then if integral exists, yeah, an integral from 0 to t AU, DW, the martingale. So there is a technical condition.
Well, I got.
So there is a technical condition. We are not checking it because otherwise it will. So like with Dup's theorem, it's a good idea to know Dup's theorem. It's a good idea to know that many stochastic integrals are martingales, with some small exceptions for those who have a big expected value. But it would be so. In many cases, we have studied. We can calculate even that, because so in sometimes we can even check. It would require more work, but in general.
But thus we assume that it exists, right? While solving.
Yeah. We are not introducing stochastic integral rigorously. So my introduction is not rigorous because I have assumed when we have derived the integral from 0 to t wu dwu, we have subdivided time interval into n equal intervals. And in a rigorous honest definition, we need to prove that the answer does not depend on the way how we divide into small intervals. The main thing in definition of a stochastic integral is that the length of these segments should go to 0, but they may be of different lengths. And
Okay.
we have not. So we have simplified the definition a little bit, like, well, let's divide for equal parts.
Thank you.
Okay. Okay, let's solve some more questions. I think it's worth to do it. Let me check something. Okay, let's solve some question from past exam.
Maybe something with Dup's theorem.
Okay, let's do it.
Can we also solve something with Black-Scholes model if we have time, please?
Yes. Yeah.
And maybe also stochastic differential equation, something difficult.
Yes. Yes.
But it's just Dup's theorem. It's just the same as the optional stopping time theorem.
Yeah, exactly. Okay, let's solve number 5 from last exam. So we have winner process WT, and we have a line 10 minus t. This line goes like that. And we are interested in a first moment, so it's number 5 from past exam.
It's 10 minus t.
Yeah, 10 minus t. So there is a first moment, then we will touch this line. Let's call this moment t. And the main question of the exercise is to find expected value of t, tau, and variance of tau. Okay. And there are, so this is rather hard exercise because boundary crossing problems are rather hard because it has to do, so why they're useful? They're useful because there are types of option like knockout option. So they're not European type, but just when you, if you will study some more complex options, then there are options that you will receive $1 if the price never goes above of a share, if the price of a share never goes above 100 rubles. So basically, this is useful for evaluation of knockout options and financial derivatives like that. Okay, so there are hints. So I will go hint by hint to show you that from this, it's very difficult to do this problem from scratch. And I try to provide, so I don't like to avoid the complex problems, but I try to provide some guiding steps. You may completely ignore them. So I write something like, you are free to use or not to use the following hints. So if you go that way, you are graded partially. If you choose so if you choose another way, so you will receive full credit if you solve the exercise. If you do some steps, you will receive partial credit. Okay, so first,
may I ask, so in our homework in this task, point A would be just like this hint for point B?
Sorry.
We have problem 4 on Dup's theorem as well. So here, like in past exam, you provide the function so as a hint. Yes?
Yeah.
So should we consider the function in A as well as a hint for B, or?
You may consider. You may consider. You may consider. You may not consider.
Okay, but this is kind of a hint, right? Not just like separate task. Okay, thank you.
Yeah. Because if you have a martingale, you can immediately apply Dup's theorem.
Okay, thank you.
Okay, so first A we have already solved, so we will save a little bit our time because first hint says that check whether it's a martingale. And because we have just checked that, so the answer is yes. So let's go to B. If it's a martingale, then expected value of, let's call it RT, so let's apply Dup's theorem. So the second step, B, the hint B is just find what we need to find. We need to find expected value of minus lambda tau. That's a very good function. Why it's a good function, I will show you in a moment. I will show you in a moment why it's useful function, but let's find it. Let's call this function like it's called here, m of lambda. And let's do so by Dup's theorem. So now the solution, Dup's theorem. We have expected value of r tau is, so imagine that it can be applied. It's r0. R0 is 1. So expected value of exponent of sigma w tau is minus sigma squared tau over 2. So it is 1. Okay? Yeah?
Okay.
R0 is 1, it's given by the problem, or I missed?
No. We just, this is RT. I just have calculated it.
If it's 0, yeah. Now, okay, thank you.
Okay, what do I know? What is tau? Tau is a very special moment of time. So if the time is tau, then the winner process is at 10 minus tau, because tau is a moment when we hit the line. And so if we hit the line, then W tau is just 10 minus tau. So exponent of 10 minus tau minus sigma squared tau over 2 is 1. So basically, expected value of exponent of 10, sorry, I can move out exponent of 10.
There should be sigma, right, also, no? In front
Where?
of 10 and
yeah, you're right.
And this, I'm sorry, once again, this 10 minus t is the winner process, right? Given by the problem.
No, the problem says you can open the problem. So it once again, it's number 5 from last year. They are available. You can open the problem. So we are searching once again. The problem is WT is the winner process. Tau is a stopping time when we hit this line. The first moment when we hit the line, and the question is to find these two quantities. But when we hit this line, obviously,
yeah, the value is W tau 10. Yeah, okay. Thank you.
Oops. Okay, now it is sigma, I forgot there, and here I have exponent of minus tau times sigma plus sigma squared over 2. One, two, three, and it's 1. Okay. Yeah. Any questions?
No.
No questions so far.
Okay, so expected value of exponent minus, so I will put it lambda instead of this guy, is exponent minus 10 sigma. Okay.
Okay.
And if I know that sigma plus sigma squared over 2 is lambda, I can solve for sigma. Sigma squared plus 2 sigma is just 2 lambda. Sigma squared plus 2 sigma plus 1 is just 2 lambda plus 1. So sigma plus 1 squared is just 2 lambda plus 1. So sigma is either sigma plus 1 is either square root of 2 lambdas plus 1, or sigma plus 1 is minus square root of 2 lambdas plus 1. And in this case, sigma is minus 1 plus 2 square root of 2 lambdas plus 1, and this one is minus 2 square root of 2 lambdas plus 1. I assume in my case that, let's assume that sigma is positive. So I don't care, but let's for the moment assume it's positive. Sigma is positive. Let's assume. And in this case, expected value of exponent of minus tau sigma is exponent of 10 plus, sorry, so I take the first root. I take the first root. I multiply it by 10 because I need to multiply it by minus 10, yeah? And it will give me 10 minus 10 square root of 2 lambdas plus 1, okay?
Clear?
So this is the answer, right?
Yeah. So
Well,
sorry.
This is the answer, right? Final
This
answer.
is the, not the final answer, but
It's the answer to the question finding the expectational exponent of this expression, right?
yeah, it's answer for the hint. So if we follow the hints, it's answer for one step.
Mhm.
But then anything is easy. So imagine that I know this function. Yeah, it's some function m of lambda. Yeah, let's describe the function m of lambda. Okay, I'm sure you can find the derivative at 0. Yeah. Okay. Can you find the derivative at 0?
It's 0.
Yeah. So if you know, so it's point C, I don't know. If you know, so it's very baby question. If you know the function, could you find the derivative f prime at 0, m prime prime at 0? Can you find it?
Yes.
Yes.
Yes, I believe you. I believe in you. So imagine that you have found, this is just a number, yeah, because the time is up. And I just like to finish the hard part and not the technical part, because I believe that you can find the derivative. Yeah. Okay. I can believe in you.
Yes.
If you have a function, can you find it? Okay.
You can believe in us.
Yeah. Just take derivative and plug in 0. Take derivative and plug in 0. You may use Taylor expansion. It's fast with Taylor expansion. Okay. But what is the meaning? So the final point is D. What is the meaning of f of m of lambda? It's expected value of exponent minus lambda tau. So if I take derivative, it will be equal to, I take derivative, it's minus tau, exponent of minus lambda tau. If I put m prime of 0, if I put 0 instead of lambda, I will have expected value of minus tau. Okay?
Mm.
Magic, yeah? If I take second derivative, m prime prime with respect to lambda, it is expected value of tau squared, exponent of minus lambda tau, because you just second derivative with respect to lambda. And m prime prime at 0 is just expected value of tau squared. Okay?
Okay. So the answer is that expected value of tau is minus m prime 0.
Yeah, and the answer is that expected value of tau is minus m prime of 0, and I believe in you that you can take derivative. And variance of tau is just expected value of tau squared minus expected value of tau, and it is m prime prime at 0 minus m prime 0 squared. And it's up to you to do the technical stuff to calculate the derivative of a function. Okay?
Thank you.
Okay, so bye-bye. Have a nice day.
Thank you.
See
Bye.
you next time.
Okay, thank you.
Thank you.